Welcome to section 4.2, differentiating inverses and compositions. We are using the text Advanced Calculus by Patrick M. Fitzpatrick, second edition. This is Dr. Gilbert, Eyabi. Introduction. In chapter 3, we saw the following theorem. Let I be an interval and suppose that the function f from I to R is strictly monotone. Then we concluded that the inverse function f inverse, whose domain is f of I, and the codomain is R, the set of real numbers, is continuous. Now let's play with that a little. Suppose we define J to be f of I. Now we know f inverse exists, so we are looking at f inverse going from J to R. But if f is differentiable at the point x0, x0 is from I, and of course this function is continuous, x0 is from I, we can talk of f of x0. So f of x0 is some point y0 in J. So we ask the following question. Since f is continuous, f is differentiable at x0, f inverse exists, it is continuous, what about the differentiability of f inverse at the point y0? And in this section, we will show that yes, f inverse is differentiable at y0. Now let's look at this a little closer. F is a mapping from I to f of I, which is J, and that's a subset of R. That's the range right there, or the image. F is strictly monotone and differentiable at the point x0. Of course, because it is differentiable, we know it is continuous. Now, let's go the reverse direction. F inverse is a mapping from J to I, which is a subset of R. And x0 is a point in I such that y0 equals f of x0. So the conclusion here is that f inverse does exist at the point y0, and we shall find exactly what f inverse prime at y0 would be. And that is theorem 4.1.11. So let I be a neighborhood of x0 and let f from I to R be strictly monotone and continuous. Suppose f is differentiable at the point x0 in I and f of x0 is non-zero. Define J to be equal to f of I as we have seen before. Then we can talk of the inverse of f from J to R being differentiable at the point y0, where y0 equals f of x0, and the formula f inverse prime at y0 equals 1 divided by f prime at x0. So, wait a minute. What we are saying is that the first derivative of the inverse at the point y0 is simply 1 divided by f prime at the point x0. So if we know two things, if we know the x0 such that f of x0 equals y0, and if we know the first derivative of f, then the first derivative of the inverse of f at the point y0 is just 1 divided by f prime at x0. So what is our goal? Our big goal is to find x0 in I such that f of x0 equals y0. And this is advanced calculus, so by now you shouldn't have any problem with derivatives. You can close your eyes and differentiate whatever I give you. So the first derivative, plug in your x0, the reciprocal of that is the derivative of f inverse at the point y0. Interesting. Let's go ahead and look at the proof. Proof. Since x0 is in I and J is f of I, it follows from the intermediate value theorem IVT that J is a neighborhood of y0. And remember, y0 equals f of x0. And because f inverse exists, let's just put this down so that we know where we're going. If our y naught equals f of x naught, it means x naught is the same as, I can move my f over, f inverse of y naught. So have this with you as we move on. Now, pick an element y from J where y is different from y naught. We're heading towards the first derivative, the formula involving limits. Then there exists an x in I such that y equals f of x. That's not rocket science. That's simply because f goes from I to f of I, and f inverse goes the reverse direction. So y equals f of x. And again, you can see here that your x would just be f inverse of y. So why don't we concentrate with f inverse? Because we're interested in the first derivative of f inverse. And from section 4.1, we know the definition of the first derivative from first principle. Okay, limit as x approaches x naught, f of x minus f of x naught divided by x minus x naught. So hopefully that is still fresh in your mind. So let's get back here. So we look at f inverse of y minus f inverse of y naught divided by y minus y naught. We're heading somewhere. So that equals, wait a minute, f inverse of y is simply x. F inverse at y naught is simply x naught. Interesting. And y is simply f of x. And y naught is simply f of x naught. So plug all of that in and we have x minus x naught divided by f of x minus f of x naught, and flip that over. 1 divided by all of this. Oh, interesting. F inverse is continuous. So limit as y approaches y naught. We are picking at y as y approaches y naught because the first derivative of f inverse at the point y naught is going to be limit as y approaches y naught. So let's go ahead and look at that. So the limit as y approaches y naught of x would simply be the limit as y approaches y naught of f inverse of y, and that is simply f prime at y naught. Again, recall the definition of continuity. Simply put, x approaches x naught, f of x would approach f of x naught. So f inverse continuous, do the same thing. Y approaching y naught, f inverse of y would approach f inverse of y naught, but f inverse of y naught is x naught, right here. Okay, now that we have this nice little line down, let's go ahead and enjoy our game. So f inverse prime at y naught would be the limit as y approaches y naught, f inverse of y minus f inverse of y naught divided by y minus y naught. But all of these, we just did our little algebra. All of that is simply the limit as y approaches y naught of 1 divided by this quantity right here. But this quantity right here, by the quotient limit theorem, if I move my limit, that will be limit as y approaches y naught of 1 divided by limit as y approaches y naught of all of these. And all of this is simply f prime at x naught. So f inverse prime at y naught simply equals 1 divided by f prime at x naught. And that follows from the quotient limit theorem, the composition limit theorem, and the constant limit theorem. Remember the quotient limit theorem, the constant limit theorem, and the composition limit theorem? In other words, the limit of the quotient is the quotient of the limits. And same thing with the composition, and same thing with the constant. And that brings us to the end of our theorem 4.11. And that beautiful, interesting, elegant theorem has been proven. The first derivative of the inverse at y naught simply equals 1 divided by f prime at the point x naught. Again, our focus would be to find this x naught. And we'll do some of these when we look at practice problems in class. And if you are not in my class and you're using Fitzpatrick's book, there are a couple of examples at the end of this section where you can get your x naught just by observation. Happy solving. Let's move on to corollary 4.12. Now, if we consider the inverse function as the primary object, then we denote the variable it depends on by x, and then we have the following corollary, 4.12. Let I be an open interval, and suppose that the function f from I to r is strictly monotone and differentiable with a non-zero derivative at each point in I. And again, if we define our j to be f of I, then we can talk of the inverse function. F inverse from j to r would be differentiable, and the first derivative of f inverse is simply 1 divided by the first derivative of f inverse of x. And there is a parenthesis here which we have omitted, so please make sure to put the parenthesis right here. Sorry about that. I'm very particular with parentheses, so when I miss one, I don't like it. So let's look at it right here. What we have is that f inverse prime at y naught equals 1 divided by f prime at x naught. That is our theorem 4.11. But observe that y naught equals f of x naught. So x naught is simply f inverse at y naught. So instead of x naught, if we replace that with f inverse at y naught, then theorem 4.12 is simply f inverse prime at y naught equals 1 divided by f prime at f inverse of y naught. And we have our two parentheses here, so we're good. Sorry about this one, but it's right here. So if we replace our y naught by x, since that is the variable it depends on, then we have f inverse prime at x simply being equal to 1 divided by f prime at f inverse of x. Again, we have all our parentheses in place here. Okay, so that's the easy look as far as the corollary is concerned. Now let's just put that into a more formal proof. Since differentiability implies continuity, and we know that f is differentiable, we can conclude that f from I to r is continuous. So we can apply theorem 4.11, which we just saw above at j, in which case our x is f of f inverse at x. Observe that that's going to be the case because f composed with f inverse is just I. So that is x. So in this setting, f inverse plays the role of x naught. And in theorem 4.11, we have that f inverse prime at x simply equals 1 divided by f prime, f inverse of x, and all the parentheses are in place. And that happens for every x in J. And we're done. You see why I like the little explanation on the right-hand side? It kind of makes the proof not so abstract. Thank you very much. That's the conclusion of that proof. Now let's go on and look at some more interesting things. Next, we would look at proposition 4.13. Let n be a natural number. That means n is greater than or equal to 1. And let g of x be defined as the function x raised to the power 1 divided by n, where x is greater than 0. So the domain is going to be 0 to positive infinity. And the codomain, of course, is the set of real numbers R. Then we conclude that g is differentiable at the point x, and its first derivative is given by 1 divided by n, x raised to the power 1 over n minus 1, where x is greater than 0. Why is this interesting? Back in section 4.1 that deals with the algebra of derivatives, we saw that if f of x is x raised to the power n, then its first derivative is simply n, x raised to the power n minus 1. As a matter of fact, we only proved it very rigorously in section 4.1. The first time we saw this was in calculus 1 when we started doing derivatives. So we are all very aware of the first derivative of x squared, of x cubed, of x to the power 5. Okay, that's pretty straightforward. But what we are saying here is that if we raise x to an exponent that is different from n, in this case 1 divided by n, then x raised to the power n, if I take the derivative of all of that, it still follows the rule of x to the n. And the derivative would be 1 divided by n, x raised to the power 1 over n minus 1. That obviously deserves a proof. So let's go ahead and look at the proof. Let's define f from the domain 0 plus infinity to r by f of x equals x to the n, x greater than 0, familiar territory. The first derivative is just n, x to the n. Now consider g that is given above. I want you to observe that g composed with f is simply going to be ia, which means g composed with f at the point x is just going to be x, and f composed with g at the point x is just going to be equal to x. What does that mean? We've mentioned this over and over again. If g composed with f is ia and f composed with g is ia, that means that the inverse of g is f. Okay, remember? That's what inverses are. So the inverse of g is f. So we're going to treat this using our corollary above and our theorem above. So let's continue. Again, as a reminder, the first derivative of f is just n x raised to the n minus 1, where x is greater than 0. So as we saw up here, f is the inverse of g, or g is the inverse of f, whichever way you want to put it. So g prime at the point x, and remember that our target here is to find the first derivative at g. So the first derivative of g at the point x is simply the first derivative of f prime. Remember, g is nothing but f inverse. So f inverse prime at x. But what is f again? F is x raised to the power n. Keep that in mind. Let's continue. So by corollary 4.12, the first derivative of the inverse of f is going to be 1 divided by the first derivative of f, parentheses, f inverse of x. But what is your f inverse of x? Your f inverse of x is simply g of x. Remember the relationship between f and g. Beautiful. But wait a minute, what is f prime? F prime is n x raised to the n minus 1. So plug that in. That will simply be n, that is your g of x right there, raised to the n minus 1. So that equals 1 over n times x raised to the 1 over n minus 1. You're like, whoa, is that for real? Hold on, let's go very slowly. Recall that g of x equals x raised to the 1 over n, x greater than 0. So x to the 1 over n, all of that raised to the n minus 1. We are interested in just this quantity right here. That equals x raised to the n minus 1 divided by n, which, simple algebra, that is x to the 1 minus 1 over n. Okay, now let's bring in the 1 divided by the denominator. So 1 divided by the denominator equals 1 divided by n times 1 divided by all of this. But what is this? All of this. You know the rule. 1 divided by a to the n is the same as a to the negative n. So that is 1 divided by n times rules of exponent, x raised to the negative. Remember, we just saw that all of this is the same as all of that. So negative 1 minus 1 over n. But what is negative 1 minus 1 over n? We just flip that. So that becomes 1 divided by n minus 1. And so that equals 1 divided by n times x raised to the 1 over n minus 1. And therefore, we can conclude that the first derivative of g at x is simply 1 over n times x raised to the 1 over n minus 1, where x is greater than 0. And that brings us to the end of the proof. Elegant, beautiful. So many x's and n's and the rest. I hope I didn't make an error somewhere. We now move on to the chain rule. So we have seen differentiation of inverses. Now let's look at the chain rule. We have already seen that the composition of continuous functions is continuous. We got that from the composition limit theorem. Now we want to show that the composition of differentiable functions is actually differentiable and provide a formula for it. And that is known as the chain rule. Again, you've seen this back in Calculus 1. We're just going to bring it back here and then ask you to study the proof. So let I be a neighborhood of x0, and suppose that the function f from I to r is differentiable at the point x0. Let J be an open interval such that f of I is a subset of J, just like we defined before. So f goes from I to f of I, that equals J, which is a subset of R. Suppose that the function G from J to R is differentiable at the point x0. Then we can talk of the composition G composed with f from I to R, and we say the composition is differentiable at the point x0, and the first derivative of the composition G composed with f at the point x0 is G prime of f of x0 times f prime at the point x0. So if we were to explain this, what you want to do is you differentiate f and you differentiate G at arbitrary points. Then you evaluate f prime at x0, evaluate f of x0, and then evaluate f prime at f of x0, multiply both, and that gives you the first derivative of the composition G composed with f at the point x0. The proof, I'm going to leave that as a sieves. Before now, sieves stood for simple exercise for serious students, but because of the length of this video, I'm going to leave it as serious exercise for serious students. So go to your textbook, Advanced Calculus 2nd edition by Patrick M. Fitzpatrick, pages 99 to 100, and study that proof. We will discuss it in class. So let's recall what we said about differentiating compositions, G composed with F. So G composed with F at an arbitrary point X, the first derivative of that. So what do we do here? We compute F prime and then simplify that. We compute G prime and simplify G prime at the point F of X. Then we multiply G prime at f of x times f prime at the point x, simplify, and then evaluate at the point x0, and that gives us G prime f of x0 times f prime at x0, and that is our first derivative, G composed with f at the point x0. The proof, I will leave that as a sieves. Serious exercise for serious students. And we close with proposition 4.15. Interesting. So far, we have seen that if I define f as x raised to the power n, then the first derivative is simply mx raised to the n minus 1, or nx raised to the n minus 1. If I define it as x raised to the power 1 over n, then its first derivative is 1 over n, x raised to the 1 over n minus 1. Interesting. So a natural question is, what if I do not raise it to either n or 1 over n? What if I just raise my x to the power r, where r is a rational number? At least we want it to be rational. Irrational numbers is a whole different ball game. So what if I raise it to the power r, where r is a rational number, and again our x is bigger than 0? Yes, h is going to be differentiable, and the derivative is still the same thing. It's still rx raised to the r minus 1. That's interesting. And yes, it does merit a proof. So let's look at it. R is rational, so r in Q means that I can find integers m and n, where n is strictly bigger than 0, such that r equals m divided by n. Okay, that's the definition of a rational number. And precisely here, I need a couple of things. I want my n to be greater than 0, so I can have r equals m over n. Now, for x greater than 0, let's define a couple of functions. Define f of x to be x raised to the m. We already know what the derivative would be. Mx to the m minus 1. Now, define g of x to be x raised to the 1 over n. We now know what the derivative would be. 1 over n, x raised to the 1 over n minus 1. I want you to observe that h of x, which will be h of x equals x raised to the m over n, is just going to be a composition of these two functions. Let's go slowly. As we have seen before, f from the domain 0 infinity to r is differentiable, and its derivative is giving us this, and its derivative is giving us this for x bigger than 0. Similarly, from proposition 4.13 above, g, whose domain is 0 infinity to r, is differentiable, and its derivative is given by this, again, x greater than 0. All we need to observe here is that g composed with f is going to be your h. And I need you to verify that very easily. Verify that g composed with f is simply going to be x raised to the power m over n, which is simply x raised to the power r. So the first derivative of h at the point x simply equals g composed with f prime at x, and by proposition 4.13, that is simply g prime at f of x times f prime at x, and then we go slowly. The first derivative, okay, again, how is g defined? G is 1 over n, so that is 1 over n, x to the 1 over n minus 1. So that would be 1 over n, what I have in here, which is my f of x, and f of x is x to the m. So that would be 1 over n, x to the m, raised to the 1 over n minus 1. And then the first derivative of f, again, is m, x to the m minus 1. Plug that in. Multiplication, simple algebra. And you shouldn't have any algebra questions at this time. Well, at least if you have some, you can answer them. Or you can email me or text me or Skype me or tweet me or whatever it is. So let's continue. Now you can move your m over. That gives you m divided by n, x raised to the, this portion right here is simply m divided by n minus m. And this portion right here is simply x to the m minus 1. Remember, this m moved over here and now fellowships with n. And rules of exponent, x to the n times x to the m is just x to the n plus m again. So just do a little algebra here, and that gives us x to the m over n minus 1. But wait a minute, what is m over n? M over n is r, so that gives us r x to the r minus 1, where our r is m over n. Again, our n is bigger than 0, so we are not worried about anything disappearing on us. And that brings us to the end of that beautiful proof and to the end of section 4.2, differentiating inverses and compositions. Thank you very much. God bless you, and I will see you in section 4.3.